I would highly expect to see a question like example number 2. I've seen this quite recently, so this is a good question, and it has a lot of different concepts involved in it. You're given some values here. You're given delta H for the reactants and the products, and you're also given delta S values for those as well. So we'll do some stuff with that, so make sure that if you're given those values, hey, go ahead and use them. Let's go ahead and get right into that. All right, part A. So it says octane gas is used in gasoline. Use the data below to answer the following question. So part A says, write a complete balanced equation for the combustion of octane. Assume carbon dioxide and water are your only products. All right, now, here's what I would like for you to do while working these out. Don't sit here and watch me do it. Actually try it. In other words, it doesn't benefit you at all to sit here and watch me do it. Now, we all know how to balance equations, so do it. Hit the pause button, work it out, and then check your work. You should be doing this with any and all videos, but again, I have a feeling that some of you have just been sitting and staring at these. All right, so hit the pause button. Go ahead and write out the balanced equation for the combustion of octane. All right, hopefully you've already finished the balancing. And then my pen will work here. So oxygen. And again, in all combustion reactions with a hydrocarbon, you will always form carbon dioxide and water. Always. No ifs, ands, or buts. All right, the first thing that I want to notice is I have hydrogen that has 18. Not a very good idea to put a 9 there, unless you plan on using fractional coefficients. Now, a lot of you don't use fractional coefficients, so don't do that just yet. So, always have an even number in front of the water. So, I like the 9, but go ahead and double that. So, we'd have an 18 there. Okay, so that means that I need 2 octanes. So how many carbons do I now have? 16. So I need to put a 16 there. All right, so 16 times 2 is 32, plus 18 times 1 is 50. We had no oxygens in the octane, so we need 25 oxygens. All right, and again, a couple things about balancing hydrocarbons. If you didn't have me in class, even numbers in front of the water, save the oxygen for last. Even number in front of the water, save the oxygen for last. And you'll notice that oxygen's in both of these, so we don't want to try to balance the oxygen first and foremost. Now, some of you would have said, well, you know, I kind of like fractional coefficients. And if you like fractional coefficients, then you can go ahead and make that a 1, make that 25 over. You can make that a 1, you can make that 25 divided by 2. Make that an 8, and you can make that a 9. So if you're doing fractional coefficients, this is what you would need to do. So whatever 25 divided by 2 is. All right, so what is that, 13 and a half, 12 and a half, 12 and a half. Okay, so that's your call. I personally don't like fractional coefficients, but again, it doesn't really matter what I like. Okay. All right, so we got the first part done. Let's look at part B. Calculate the standard enthalpy change. So again, we're looking at delta H, and it will be the products, sum of the products minus the sum of the reactants. Okay, do I have enough room to do it? Yeah. So we need to, so here's our reaction, so here's our products, and here's our reactants, and we do want to use the balance equation to answer this. So delta H is equal to 16 carbon dioxide, whatever the value for carbon dioxide is, negative 393.5. Sorry, I'm going to be scrolling back and forth. 393.5, and that is kilojoules per mole. Plus, come on, plus 18 times a negative 285.8 kilojoules per mole. And that's all the products. And then we're going to do 2 times octane. And octane is negative 208.4. If I start writing smaller here, I apologize. That's kilojoules per mole. Plus, now again, oxygen doesn't have a value and don't have to give that value. Hopefully you realize that for delta H and delta G, anything in its elemental state at room temperature, and oxygen is a gas at room temperature, will have a value of 0. But I'll go ahead and show it. So 25 times 0 kilojoules per mole. Okay, and block that off. Okay, so when we type all that in, delta H is around negative 11, 23.6 kilojoules per mole. Now, what does the question ask? It wants to know what is the standard enthalpy change for combustion of 1 mole of octane gas. Now, from our balanced equation, how many moles of octane are we looking at? Hopefully you recognize that there's 2 moles in this balanced equation. So what we need to do is divide this by 2, because again, we're using, at least I did, unless you did fractional coefficients, then you're good to go. However, since I used the 2, I used the 25, I used the 16, I used the 18 instead of the fractional coefficients, I have to divide it by 2. If my octane, say it had a coefficient of 5, I would need to divide it by 5. So when I divide it by that value, I get a negative 55, 11.8. Okay. Now, again, that still means that this reaction is exothermic. It's a good start. That's good. Again, remember our situations from the first video. Exothermic is a good deal because now that starts off our delta G with a negative sign. So now we want to find and calculate the delta S for the combustion for 1 mole of octane. So hopefully you realize what you're going to need to do here. And again, same thing, products minus reactants. And you should have values for every single one of these things since we are at 25 degrees. Alright, so we have our values there. So we're going to try to write small here. And this has a little bit of a different value, or unit, I'm sorry. So we have 16 carbon dioxides, which has a value. And again, we're looking at this column. Carbon dioxide is positive 213.7. And that's joule mole per Kelvin plus 18 waters, and I have 188.8. So 18, 188.8, and that's joule per mole Kelvin. Okay, and that's all of our products. Minus, we have 2 octanes, and octane has 345.3. Joule mole Kelvin. And then we have 25 oxygens. And oxygen will have a value because, again, it is a gas at room temperature, so 205.1, which means it has some disorder, which is good. And it is very random. So 1 joule mole Kelvin. And that's everybody. So let's go ahead and do that. And my unit will be in joules over mole Kelvin. And when I type all that in, I get a positive 999.5, and that's joules per mole Kelvin. Okay. Now again, we're still looking at 2 moles of octane, so divide that by 2. And when I do that, I get a positive 499.75. Alright. Now, again, delta S has a positive sign. What does that mean? We are increasing the disorder. Now, let's double check that. When we look at our balanced equation, how many things do we have on the right? Well, we have 16 plus 18. I believe that's 34. So we have 34 products. And then we have 25 plus 2, which is 27. So, yeah, that is getting more disordered or more random, which is a good thing. So our signs are consistent here with our spontaneity. I'm sorry, not our spontaneity, our disorder. All right, so now we're going to determine spontaneity. So we have a delta H and we have a delta S value. So let's plug those in. So we have delta H minus Okay, now, first and foremost, delta G wants to be in kilojoules per mole, and I have joules per mole over here. So let me go ahead and convert that real quickly. So there's 1,000 joules in a kilojoule, which means that that is now a 0.49975 kilojoule per mole Kelvin. Okay, so we did that. All right. Sorry if it's getting sloppy here. I wish this pen would work better. All right, so let's calculate delta G. So delta H, which was from up here, we have a negative 5511. 5511.8, again, kilojoules per mole. And then we're going to subtract that from our temperature, which is, I believe, at 25 degrees. Okay. So change that to kelvins. So 298. And then our delta S, which we just changed to the correct units, for 0.49975 kilojoule per mole Kelvin. Okay, and again, kelvins cancel out. Now we can subtract the like units. So delta G, type all that in. I get a negative 5,661 point, I'm not sure what, and that's kilojoules per mole. Alright, so now let's ask ourselves the question: should we have expected a negative delta G? Theoretically, yes. Again, it doesn't matter what the temperature is because we have an exothermic reaction. We have an exothermic reaction from our data here, and then our delta S has a positive sign. So again, our positive sign means that, okay, at any temperature, this reaction will be spontaneous. All right, hopefully you'll have a few more examples like this on the homework. As always, I hope this video has helped.